Welcome to my presentation about the generation of virtual three-phase structures based on Gaussian random fields. I will illustrate this approach for digital materials design of solid oxide fuel cell electrodes. As an introduction, I will present the methodology for digital materials design for SOFC electrodes. To optimize such electrodes, you need to establish a relationship between the fabrication parameters you can tune and the electrode performance. Experimentally, you can do this by fabrication and characterization of the cells. To get more insight, you can reconstruct the 3D microstructure using tomography. With quantitative image analysis, all the relevant microstructure characteristics can then be determined and the effective properties can be deduced. These effective properties can also be determined directly using 3D simulation on the 3D microstructures. For this virtual materials testing step, we have fully automated scripts in GeoDict. To get then from the effective properties to the cell performance, we use multi-physics model, which includes all the relevant physical effects for this performance prediction. To then close the loop for a fully virtual optimization, we also need to be able to create realistic virtual microstructure, and this we do with stochastic modeling. And therewith we have closed the loop for a fully digital materials design, and we can do optimization loops which with much more parameter studies that it would be possible with only experimental methods. In this talk, I will focus on the generation of virtual 3D microstructures with stochastic modeling. Solid oxide fuel cells are electrochemical converters to produce electricity directly from oxidizing a fuel. Here you see the example for hydrogen, but there is a large flexibility to use different fuels, for example natural gas or biogas. A solid oxide electrolyte is used, which gives this device its name, and it is operated at high temperatures, typically at 850 degrees Celsius. In this study, we will focus on the microstructure of the anode side. SOFC anodes are usually three-phase systems with two solid and one pore phase. An appropriate digital twin for such a system needs to fit all the decisive microstructure parameters for this application. And I will specify these parameters in the following. First, for the pore phase, here you have gas transport, which is governed by bulk and Knudsen diffusion. For the Knudsen diffusion, also the characteristic pore diameter is an important parameter. Then for the charge transport, we have either ionic or electronic conduction. So for the microstructure side, the relative electronic conductivity of nickel and the relative ionic conductivity of Ni-YSZ is of importance. The hydrogen oxidation reaction takes place at the three-phase boundaries, and therewith the lengths of these 3pp lines are of importance. These 3pp lengths are a very important parameter for the kinetics of the reaction. The ceramic composite anodes are an alternative concept, for example with an LST perovskite and ZHAW. Of course, for the pore phase that's the same, but for the charge transport it's different because both of these phases are mixed ionic electronic conductors. That means both phases conduct to some extent the ions and the electrons, and therefore the relative composite conductivity is of importance. The reaction takes predominantly place on the two-phase boundary of ZHAW, so the ZHAW pore interface area is a very important parameter for the kinetics here. And again, for a good digital twin, all of these parameters need to be fit quite accurately. Here you see a 3D tomography example of a Ni-YSZ electrode from Holzer et al. In the 2D autoslice, you see quite well that both phases build quite continuous networks, and that the original particle geometries from the powders are no more really visible. This is due to the sintering. Okay, we now want to model such a microstructure, and if we do that with sphere packing algorithms, it's quite hard to get these continuous phase networks, and also the related microstructure properties are hardly matched. Of course, it can do better than here shown in this picture, but I think you see the point. You need to force this particle system to something continuous, and this will also be computationally expensive. An alternative approach is to use Gaussian random fields as a base for the structure generation. And you see, here you get continuous phase networks from the outset, and it's also quite computationally efficient. Moreover, you will see later that also the microstructure properties match quite well. This Gaussian random field approach for the structure generation of SOFC electrodes was introduced by Musao et al., and we now implemented it in GeoDict in order to have the full workflow with structure generation and characterization within one software. For this approach, you start with two Gaussian random fields, one for each solid phase. First, what is a Gaussian random field? It is a volume field with a field variable that takes random values between -4 and 4, and this in a way that its correlation function corresponds to a truncated Gaussian distribution. The standard deviation of this Gaussian distribution is chosen to correspond to the typical pore or particle size. Or in other words, the distance between two of these red peaks corresponds to the distance between two strands of one solid phase. You see, these random fields are continuous fields, so to get to well-defined separated phases, you need to apply threshold operations according to the needed volume fractions and wetting behavior. Here you see the results with two solid phases and one pore phase, which is simply the space left, which is not occupied by one of the solid phases. In the following slides, I will show some examples of the thresholding. Here you see the thresholding plane. On this axis, the Gaussian random field 1, and on this axis, the Gaussian random field 2. This plane is now divided into three sectors, one for solid phase 1, for solid phase 2, and for the pore phase. The integral values over these sectors then corresponds to the solid volume fractions. For this example, that yields the same volume fraction for phase 1 and phase 2 and a porosity of 25%, which corresponds to this quarter here for the pore phase. If we now want to have a lower porosity than here, we simply decrease the section for the pore phase, and we have a lower porosity of 15%. If we want to get higher porosities, we increase the section for the pore phase, and we got higher porosities in this example 50%, and still the same solid volume fraction for phase 1 and phase 2. To get a certain composition of solid phase 1 and solid phase 2, we choose corresponding areas of the sectors, and here you see the result. In this example, we have a higher volume fraction for the solid phase 1, here red, and a lower for solid phase 2 in green. The wetting behavior of the phases can be controlled by the angles between these sectors. Here you have two examples. First, the de-wetting case, where the two phases touch only rarely, and here the wetting case, where the two phases are connected quite well. It is important to mention that all these variations can be done on the basis of one single set of Gaussian random fields, and all the variations with different volume fractions and wetting behavior can be achieved only by the thresholding. This is one reason why this method is quite computationally efficient. If a Gaussian random field structure needs to match specific tomography data, the following steps are needed, which I will illustrate for the Ni-YSZ electrode. First, the correlation functions for the two separate phases needs to be determined. Then you need to construct two Gaussian random fields with corresponding correlation functions to the nickel and YSZ phase. With the thresholding operations, you then can tune the solid volume fractions and the wetting behavior. In the nickel YSZ system, YSZ wets and encloses the nickel phase. And you see, if we apply neutral wetting for the Gaussian random field structure, this is not the case. But if we match the wetting behavior, you see that we can reproduce that this behavior that YSZ wets the nickel phase. In the beginning of this presentation, I emphasized that a good virtual microstructure needs to match the important microstructure properties for a specific application. Therefore, I will now compare for the Ni-YSZ anode the microstructure properties of the tomography. This is here the blue bars. Then for the Gaussian random field with neutral wetting, and for the Gaussian random field structure with matched wetting. For the length of the three-phase boundaries, the Gaussian random field structure only match well if this wetting behavior is taken into account. Also, for a specific interface area between the phases, you see that they are quite sensitive on this wetting behavior, and they match only well if this wetting behavior is taken into account. On the other hand, for the relative conductivities of YSZ and nickel, you see that they are less sensitive on this wetting behavior. In sum, the Gaussian random field structure with the matched wetting shows a very good agreement with the tomography data. However, this could be further improved by using automated algorithms for this matching. For the ceramic composite anodes, the composite conductivity is an additional important parameter. In the conventional nickel YSZ anode, you have electron transport only in the nickel phase and ion transport only in the YSZ phase. In the LST ZHAW system, this is different because both are mixed ionic electronic conductors. That means they conduct ions and electrons both, at least to some extent. And this means that bottlenecks and islands are less restrictive for the conductivity than in the nickel YSZ system, where islands are simply dead. As a result, we have for the identical microstructure a higher relative ionic composite conductivity for the LST ZHAW system than the relative ionic conductivity in the nickel YSZ system, and the same for the electronic conductivity. As we now have a stochastic structure generator providing the right microstructure properties, we are now ready for parameter studies. In the following, I will show you a first small parameter study with Gaussian random field structure with equal particle sizes and neutral wetting behavior. That means this data is not yet matched to the specific nickel YSZ system. In this parameter study, we vary the composition of the solid phases and the total solid volume fraction, or the porosity respectively. You see that already for this small study we have 44 microstructures to characterize. For these microstructure characterizations, we have fully automated scripts ready, and one full characterization of a single 3D structure takes about 8 to 48 hours. This means that already for our small study, we will wait more than once if we use sequential computing until we have our result. And for larger studies, you easily wait several months or even years until you have your results. Therefore, we use GeoDict Cloud for such studies, which is powered by KaleidoSim using massive simultaneous cloud computing. On GeoDict Cloud, you can start as many studies in parallel as you like, which simply means that your computation time is independent from the number of your parameter combinations. This means also that for studies you would need several months or years with conventional computing can be computed on GeoDict Cloud within 1 or 2 days. Here you see some results of this parameter study representing the most important microstructure properties of the Ni-YSZ system. The properties are plotted as a function of the composition. Here you have more YSZ, here more nickel, and the porosity, here it's porous, and here it's dense. This is the relative conductivity of YSZ, which is higher the more YSZ you have in your microstructure. Here you have the length of the three-phase boundary line, which is important for the reaction kinetics. Here you have a maximum at the composition about 50 to 50 and for a porosity of about 30%. This, of course, for this specific microstructure system. These are the corresponding decisive microstructure parameters for the LST ZHAW system. Here we have the relative ionic composite conductivity. And here we have the interface area of the ZHAW pore interface, which is important for the kinetics. This interface area is the larger, the more ZHAW we have, and has its maximum at about a porosity of 50%. Last but not least, the microstructure parameters for the pore phase, which is present in both material systems. These 4 microstructure parameters are needed for an appropriate description of the microstructure as an input, for example, for the dusty gas model. In the dusty gas model, the combined transport of the gases by bulk and Knudsen diffusion are modeled appropriately. You see also that all these parameters are almost independent of the composition, but of course strongly depend on the total solid volume fraction or porosity. Therewith, we have all the needed microstructure parameters and effective properties ready and available for the whole parameter space we studied. As a conclusion, we presented the generation of virtual three-phase structures based on Gaussian random fields in GeoDict. This approach is especially suited to model microstructure types with continuous phase networks. Different volume fractions and different wetting behaviors can easily be achieved by thresholding the same set of 2 independent Gaussian random fields. So this approach is computationally efficient. These Gaussian random fields are an important option for the digital materials design of SOFC electrodes because their microstructure and effective properties can be matched very well to the original data from the tomography to the original microstructure, and this in a very efficient way. The effective properties can then be used as an input for the multiphysics model. The multiphysics model helps to solve the trade-offs for the different microstructure properties to get the best electrode performance. With GeoDict Cloud, large parameter variations can be performed in a very short time. With this workflow, we have a powerful tool available for the systematic and knowledge-based optimization of SOFC electrodes. Thank you for your attention.